Okay, you're good.
Hello, everyone. Welcome to March's Belfast Go meetup. And we've got an excellent talk in store tonight. First of all, just a bit of the usual housekeeping here, thanks to our sponsors, as you can see on the screen there. We got Cloud Shuttle and Teamwork and JetBrains and myself and Vistas. But not to talk too much, but we're going to introduce Roberto Clapis, Rob Clapis, who works in security works in Google on security issues, and I've seen him talk many times at different conferences in actual 3D in real life, and his talks are always really informative and really well made and very engaging. So I'm really looking forward to this one tonight. So I will pass the screen over to Rob, and he will kick off. Okay, over to you, Rob.
Thanks, and thanks for the amazing introduction. Let me share my screen real quick. Should now be visible. And okay, so can everyone see the screen? Guess so. Okay.
Yes,
so,
I can see it now.
Just to add a bit to the introduction, who am I? Well, yes, I work at Google. I maintain some packages of the standard library in Go, and I work in the security team. And the reason why I'm giving this talk is because I like to sleep well at night, and I would like everyone else to be able to do the same in this community. So I'm going to start with some code because I'm very hands-on, and usually I learn stuff by doing it. Here is a function, very simple. Basically, it takes a string and returns an integer that represents that string. And now, if the string has nothing to do with numbers or there is an error in parsing, I just return 0. In all other cases, I just return the number. Now, this is what, 5 lines long function if we include the return. So this is simple, right? During code review, this is clear. If anyone reads this, they will be convinced that it is doing what I just said. There is more. Let's say that I want to be extra sure that I wrote it right, and I write tests for it. So when I write tests, what I do and what everyone does, we make sure that our code solves a sub-problem of this problem. So basically, instead of testing the entirety of all the integers, we just test some, and we assert that the result is correct. So in this example, I put in just 42 as an integer, a string just to see that it returns 0, some negative numbers because I want to be very sure, and also make sure that 0 comes out as 0 and that a float is invalid. This is undecided, like, what do you do? Do you return the 1 or do you return the 0? In this case, it just returns 0. And these tests all pass, and I'm happy and just go on and write other functions. And that's what I normally do. But in this case, this is a function that accepts arbitrary input. And this is a very good candidate for fuzzing or for random testing. If we talk about fuzzing, we're talking about some evolved form of testing. Don't think of it as a hacker-specific technique or something that you cannot access. Fuzz testing is just a form of testing that feeds random input, at least in the beginning, is just random input to your functions, and then it monitors the program and tries to understand how much code it can cover, how many functions are called, and it adjusts the input that it provides so that it covers more code. The monitoring is very advanced. It relies on both your assertions, and I'll show later how to assert, and on the behavior of the program. For example, if it is a very long computation, like unexpectedly long, or if there is a panic, it will catch that. Now, what you want to do when you write a fuzz test is express an invariant, some sort of thing that should always be true for the code that you're testing. Let's see an example. For my code, which was called atoy or 0, I just pass a string. So in this case, the fuzz target with the current tools is a function that takes a byte slice They're going to get more evolved. I'll get to it later. But for the time being, the fuzz target is just taking a byte slice and returning an integer. And what happens here is I call my function. If it returns 0, I assume the input is not important. So I inform the fuzzer that 0 is an integer I'm not interested in. And then I assert something. In this case, I just assert that I can go the other way around. So reconverting back the integer to a string should give me the same initial string. This seems reasonable. This is an invariant that I would like to be true for the function that I'm implementing. Sometimes it might not be, but this is just an example. And I run it, and after 3 seconds, I have 3 crashers. I already have 3 things that say that my code is not correct, that invariant is not true. Now, keep in mind that this means that 3 different kind of inputs and crash were produced. Now, this tells us 3 things. First, that I'm awful at writing unit tests. Second, that even the simplest looking functions are not that simple to test if they accept arbitrary input. And the last thing is that fuzzing is actually surprising. Fuzzing can give you results that you don't expect. And in this case, the results are a number that starts with 0, which of course, when rendering back to a string, will lose the leading 0. A number that starts with a dash and a 0, so a negative number that has a 0 somewhere between the minus and the first digit, and then a very high number, because that overflows. And this tells us even more. Like if we fuzz on 32-bit or 64-bit, that will give us different numbers, because depending on the architecture, string convert will return potentially different results. And this was after 3 seconds of fuzz testing. So if you're wondering why you should write fuzz targets, the first reason is complexity is hidden and almost always hard to detect. Humans are not good at elaborating and finding edge cases. Most of the time when we think edge cases, we go by experience. Like for example, if you're dealing with numbers, we go towards 0 or towards infinity. And if we're dealing with strings, we try very long ones, some that contains a 0 somewhere, or like when parsing JSON, we try to put a closing brace. But this is just experience. It's not like we're inventing new stuff. We're just going by memory. And this is dangerous because our code is going to get any arbitrary input. So the best way to express something in addition to unit tests, fuzzing does not replace unit tests by any means, but in addition to unit tests, what you can do is take the assumptions that you have in your head while you write the code and turn them into targets. Fuzz targets are basically these. You just write down what you had in your mind while you're writing the code. And moreover, this has proven to be effective. Like most of the important projects that I've seen have fuzz targets and they have found bugs. Even the Go standard library has fuzz targets and has found bugs because of them. And the last reason to fuzz is if you don't do it, your attacker will. Like if you're maintaining a web service and your API has a surface that is not fuzzed and you're using, well, if you're using just the standard library with NetHTTP and JSON parse, there is a good chance that we're already fuzzing it. But if you're using stuff like fast HTTP or a custom parser for whatever format you accept, someone else will find the problems for you. And you don't want that person to be outside of your company. That said, fuzzing is not easy. I mean, if you're fuzzing something that just parses a string into an int, it fit into a slide. But if you're doing something more complex, you should keep in mind that your API should be easy to unit test. In the web service example, if the only way to test your API is to spin up an entire server and then feed some data into a socket, that's going to be very hard to fuzz and extremely ineffective. You should have a way to just insulate the function that you want to send the input to and just run that one. For example, if a fuzz target has to create a database connection, it's very likely that you will never get any results. Try to keep the setup cost of your fuzz targets very small, as you would for a unit test. Like fuzzing never gets to the end-to-end or integration test kind of side of the testing world. Moreover, try to keep your targets stateless. If your targets keep state across different fuzz runs, that is going to give you crashers that you cannot reproduce. And there is very few things that are as annoying as knowing that your code has a bug and not being able to know where. That is the last thing you want, probably, talking about sleeping well at night. That said, if you're thinking, well, there is something similar, like testing quick in the standard library that does something very close to this, you're close, but not too close to reality. Fuzzing is not just feeding random input to your library. Fuzzing analyzes your code. It sets sort of checkpoints, not really breakpoints, it's more like checkpoints, and it inspects where the execution goes. So after feeding a certain input to your library, it checks how much it covered. And this metric is also exposed by the tools, so you can check if your fuzz testing is actually fuzzing properly. And then it applies smart mutations. For example, it analyzes the memory and finds if there are some strings in memory that you can use to create a new input. It flips random bits, flips random bytes, shortens and makes longer the input. So basically, fuzz testing is the smart way of testing. And I think the most important thing is that it's fast. The last time I fuzzed the NetHTTP library, after 20 minutes of random fuzzing without an initial seed, it could send completely and perfectly valid HTTP request to the parser. So it just learned HTTP by just calling a function that parsed HTTP. So this is efficient. That said, I hope I convinced you that fuzzing is very useful. And let's go to writing the actual target. There are some things that you can do before, like when your fuzz function is being called. If you know that your code will never parse anything longer than a kilobyte, you can already just check if the input is longer than that and return 0. Like the first thing that you do is inform the fuzzer, this kind of input is not interesting for me. And we're talking just about byte slices, but there are many things that you can do as soon as fuzzing supports more structured data. So you get the data in your fuzz target, you check if it is something you can fuzz on, and if so, you call your target. Now, your function that is being fuzzed should be callable in a reproducible way. So if you get a byte slice in input and you want to fuzz, for example, a cache, there isn't much you can do there. So you have to transform this, and please make it so there is no randomization involved. All the data that you use should come from the fuzz signature, from the fuzz slice. That byte slice is your only source of input. Don't use anything else. And I will describe later how this can be done. But a byte slice is everything you need. Don't use random inside your target. And then after you call your function, inspect the return value and fail. Just fail if something is wrong, if your assertion fails. This is not very dissimilar to unit tests. Also, I just realized I cannot see the chat. So if someone is writing in chat, there is a good chance I'm missing questions.
I'm keeping an eye on the chat for you, Rob. Okay. Don't worry. So far you're...
No, okay. I was able to find it and open it. Okay. Okay, so this is an example of a fuzz target with a current tooling, because there is a nice thing, which is the ecosystem is changing a bit. So this is a target how you would write it today. In a year from now, it's going to be different. I have another example later on these slides. So you take the byte slice, you transform it into some sort of input that your function can understand. You call your function, and then if something unexpected happens, you panic. This is how you inform the fuzzer that something went wrong. If you think that the result is something relevant, you inform the fuzzer, hey, this input was nice. Give me more like this, because my function could do some work, could process something. If you think that this input or input like this should never be fed again to your function, you return -1 or any negative number. 0 just means it's fine. I could do something, maybe it's not too relevant, but don't remove this from the set of inputs that I can get, because maybe it's going to become useful in a future variation. And this helps the fuzzer understand what you're trying to achieve and what you're interested in. Because maybe the fuzzer will be able to cover the entirety of the states that your function can reach, but maybe you're just interested in some of them. All the others, you assume they're valid, which could be a mistake, or you just assume that you don't care because you know eventually there will become an error and you don't care. To run this, you currently have to use an external tool. So you get this GoFuzz executable, and you get the GoFuzz build, and you have to switch in the directory in which you have your fuzz target, build it, and run it. Feel free to just interrupt it with a Control-C. It is stateful. It keeps the state on disk. So if you run it again, it will not have to do all the job again. I know this is not the best kind of user experience, but this is the best that we can get for now.
I have a question, Rob.
Yep.
Someone's asked if should fuzzing be a must or part of testing in every software ecosystem?
So you're asking a person that works in security. I might be biased, but I would say that yes. Well, depends. As most of the time in tech, the answer is depends. I would say that if your functions, if your code only works on business logic and you get already structured data and you return already structured data and you just do some logic analysis on that, fuzzing might not be the best investment of time. It will probably still find bugs, but I'm just saying it might not be the best investment. But if you have something exposed on the internet, or if you have something exposed to user-facing input, it's very useful. And if your code is not exposed to any kind of input, it's a weird piece of code. Like, it's hard to imagine anything that works without input. But in any case, everywhere that you might expect an attacker to feed data or a user to do something you don't expect, like weird interactions, fuzzing can give results. And if it is part of the testing ecosystem, in short, like I'll get later to the kind of regression tests that you can write based on fuzz targets. I would say definitely if the fuzzer finds bugs, you should add that test case to your unit tests immediately, because if someone got it wrong the first time, it's very likely that someone else will get it wrong in the future. That said, if you should continuously fuzz on like a developer machine, probably not. Fuzzing requires beefy machines, so it shouldn't be something that you do when you save your file, which, for example, I run all the tests in my projects when I save. Fuzzing on save is not an option. Going back to some examples of fuzz targets, there are many things that you can check. For serializers like JSON is very easy because you take a string, you deserialize it, you serialize it again, and then you deserialize it again, and you compare that going through this process, the thing is the same. So preserving values across different formats is very easy to assert, and it's something important because that's where probably bugs reside. And one more thing that you can check is if you always return a 0 value if the error is not nil. There are many APIs in the Go standard library that return a value and an error, and both are valid. For example, io.write, the implementation of io.writer returns 2 valid values. And that is fine if your interface asserts that, but if you don't, it's very useful, I think, that you make sure that you don't return a tuple of values that both could be interpreted. Make sure that you don't provide something that could cause bugs later on. And then, do I see another question? If you have a function that takes a single int, would you use fuzzing? Yes, depends where the int comes from. If the int is an arbitrary int that anyone can get and changes the state of your server, yes, definitely, because maybe there are some ints that you didn't consider. For example, in one of the examples that I show later, 12 was a problematic value for my code. and it wasn't in my unit tests. So why not try? I mean, might not be the best use of time, but maybe just run it for 5 seconds, fuzz it for 5 seconds and see how it goes. After all, writing a fuzz target is not very far away from writing a test, a unit test, and you probably can reuse most of the code. So just run it for a little while. One more thing that you can check is if you have a reference implementation. Most of the time when you optimize code, you have the old implementation and the new fast implementation. So it's very easy to just run both on the same input and assert that they get that you get the same output. That is the easiest and like cheapest way to write a fuzz target. Just take the old code, move it to the fuzz file, and compare the results. If you get a difference, you know something went wrong. So your code is not just faster, it's also wrong. Especially considering that writing slow code is much easier. Then you can check that state variables were not affected or that cleanups were executed, like global variables in your package. Well, first should not exist, but if they exist, they went back to the value they're intended to be in. If you use GoFuzz, you get crashes, and crashes might not be the most user-friendly thing to look into. You get 3 files per crash. The first one is the raw input. Like if you use cat on that file and you feed it to your program, so if you just read the raw data, that is what will crash the program. The quoted file is important because it gives you a Go syntax quoted string that you can just put in your unit test, in your table test, and just add one more line. And the output is what your program printed when it crashed. This is also very useful for debugging information. Now, so far, I'm just selling you fuzzing as the best thing that you can do and the best invention since sliced bread and the wheel, but it has some problems. The first one is that your assertions might not be correct and you might get thousands and thousands of crashes as soon as you start it. If that happens, just stop it because it's probably useless and try to rewrite your fuzz target to not have that assertion or correct the assertion. Which is also an interesting work that you do because you learn more about what you're actually asserting in your code and not what you think you were asserting when you wrote it. Moreover, if your coverage grows too much with the current implementation of GoFuzz, you might end up with not covering the entire code because it currently uses a hash map, some sort of quick hashing mechanism to see coverage. And if you go beyond the 5,000, which is the metric that the tool prints, you might get collisions. So you might not cover the entirety of the code, but just a bit of it. So consider fuzzing a smaller function or just break down what you're fuzzing in simpler modules. If you instead get out of memory errors or stack overflows, there are 2 possibilities. Either your code has some real issues. So like the input was a kilobyte and your program ended up using 5 gigabytes of memory. In that case, you have a bug, pretty bad one, try to solve it. Otherwise, if you see that like the fuzzer is giving you a gigabyte of memory of input and you're using a gigabyte of RAM and it crashes because your computer is not powerful enough, just limit the input. You can reasonably just tell the fuzzer to not give you more than that. Yeah, this is something I already covered. Make sure that you always add a unit test when you find a crasher because, well, first, it puts you in the mindset of test-driven development. So you just add the target and you change the code to make it so it passes for that test. And moreover, it makes sure that no one else will make the same mistake that was made in the beginning. And this, I think, kind of answers, this slide kind of answers the previous question, which is what to fuzz. Anything that accepts complex inputs, anything that can get to a wide range of states, code that was highly optimized, any code that accepts untrusted input, third-party code, just, you know, to make sure that it does what it's supposed to, and third-party code, again, with different assumptions in mind. Like, for example, making sure that it works well within your code. For example, if you take the standard library, HTTP has a read request function that is documented to be very low level and tells people to not use it until they really need. And read request does exactly what it says. It reads a request, parses it, and returns the parsed data, which is fine. But if you use it in your code and you don't add the code that the net HTTP package would normally add around it to protect it, for example, limit the input, your code will crash. So if you that API is fast, is continually fast, and is correct. We know what it does. We know it's secure. But if you run it in your server, it might not be just because it's in a different context. Here's another question. What's my favorite fuzzing success story? I have some in the slides later, and they made me realize how bad I am at unit testing. I can just give one just now, which is I was writing a cache that was supposed to be very fast and has some advanced strategies, so that if the cache started becoming too full, I would switch to a different strategy. And when switching, I would have a bug, but only if it was barely a switch, like the exact amount, in this case 12, the exact amount of data. And it was amazing to run the fuzzer for very little time and find the bug, considering that the library was running for days on my laptop and never crashed. So in seriously a handful of seconds, I found a bug that in hours of runtime I didn't find. That was pretty fun and depressing. That said, the corpus. If you're fuzzing something like JPEG, it might be nice to provide a small JPEG to the fuzzer, because the fuzzer is smart, but very advanced inputs might not be easy. So you might waste the first hours of fuzzing just to let the fuzzer understand what you're trying to, what you want. Now, this is dangerous in a way, because if you feed too much corpus, the fuzzer will spend a lot of time testing stuff that you already know it works, because it's probably part of your test sets. So try to feed it, but not too much. Like, give it something to understand the gist of your format, but not too much so that it only provides you valid input. Finding real bugs. Here are some examples. I found 2 bugs in HJSON, which is a package, a very interesting package, because it's called a human JSON, which assumes that JSON is not for humans, which is something that always I find funny, because coming from a past where XML was the cool thing, I think JSON is pretty readable and writable by humans. I just ran it by copy pasting the tests that were in the standard library for JSON, the fast targets, not all the tests. And I found a couple of crashes, and they were fixed, which made me really happy. Then I compared fast HTTP and net HTTP, and I found a bug in either, because I mean, those are 2 implementations of the same specification. So it was very easy to just parse the random input. And if both parser passed, like didn't return an error, I would just compare, for example, the URL, the parameters. And I found a lot of stuff. Like, it's, considering how used they are, it's interesting to see how many differences I found in the implementations. And some of them were vulnerabilities, so it was not particularly bright and funny moment. NetHTML is in X, is in the standard library, and it's an implementation of HTML5. Now, I don't know if you ever tried opening the HTML5 spec, but just opening it takes 5 minutes on my laptop, just opening it, because it's so complex that just parsing the HTML and rendering it in your browser takes ages. It's like, I think 12 megabytes or just markup. And of course, any implementation will have problems. So we're fuzzing it, and we find a bug like every couple of months. And there is a tracking bug that links to all the things that we found with fuzzing. It's a lot. And it's always fun to see how it grows and how much better our code becomes thanks to this. And then there is a cache I wrote. If I have some spare time at the end, I can go in details, because I linked to the fast target. And basically, I thought a cache is a glorified and lossy hash map. So I took the byte slice, I transformed it in a series of operations on the cache, like insert, remove, and refresh. So the three things that would make my cache behave differently. And I did the same on a hash map. And if something would be in the hash map and not in the cache, and the cache was not yet full, I knew that my cache was losing data that should have been there. And for example, if instead something was in my cache and not in the hash map, that would be a problem because I was just creating wrong data. So this is something very important. There is always a way to assert something simple with a simple re-implementation of what you're trying to fuzz. Now, this is some links to crashes that I found. The bottom here in the slide is the input that made HJSON crash. It wasn't in the unit tests, and it's easy to understand why. This is not something a human would try. And this is an important success story. In Go 1.13, the JSON standard library package became a lot faster. Like there was a lot of work that made it, I would say, so fast you shouldn't require anything faster. But there were bugs because when you optimize, you usually introduce complexity. Luckily, we had continuous fuzzing set up for that function, and we found it before it was part of a stable release. So we could fix it and roll it back. If you want to see some example of fuzzing, you can see stuff that I linked in these slides, and I will publish a link to the slide later. But also, there is this repository on the Vucov GoFuzz corpus. If you see that small, tiny little thing on the right, those are folders on GitHub. And those are all examples of fuzz targets. This is the stuff we use to fuzz the standard library. So you can find a lot of things there. And if your format is similar to something that is in the standard library, for example, YAML is not in the standard library, but XML is, you can take, as an example, the XML fuzzer and just change it so that you can use it to fuzz YAML. One important thing now is to remember to update these. Since fuzzing is usually done in a separate machine from the machine you're testing on, it's important that you remember to update your fuzz targets as your code updates. Now, it's very easy to remember to update your tests because they're going to fail and your CI is going to tell you, hey, you might want to consider updating the tests since you already changed the code. But forgetting to update fuzzers is very easy, and this cost Google $8K in bug bounty just for a single element that was added to the Chrome parser. Chrome is continually fuzzed, but when the portal tag was added, the fuzz targets were not updated. And so, by just fuzzing it, independent researchers were able to find 2 memory corruptions. One thing that is important is that fuzzing takes a lot of time. And you never know when it's done. It just runs. It runs forever. You don't know if you have exhausted the research space. And you don't know if you have found all the possible intricacies of your code. Because yes, the fuzzer can tell you, I've covered all the lines. But maybe a loop was only executed once. All the lines were executed. But maybe if you run that loop exactly 10 times, it would crash. So this is an example in which OpenSSL was found vulnerable to a certain thing. I'm not going to get into the const time modular exponentiation detail, but like after 1.5 years of fuzzing, this was found. And this is important because maybe you cannot afford to fuzz for that long, or maybe your project is open source, you set up OSS fuzz, you start the fuzzer, and then you start ignoring it after a while. You might get results after a long while. And at this point, there is the question, how much should I fuzz? And as my grandma always said, piuttosto che niente da me piuttosto, which roughly translates to a bit of fuzzing is better than no fuzzing. And I think this is important because I can safely say that the biggest amount of bugs that I found with fuzzing were all found within the first hour. So if you want a ballpark number, an hour, maybe less, maybe a bit more, something in that order of magnitude. If you want to know how much you should really fuzz, forever. Just dedicate one of the machines you have, maybe even an old one, and just let it run, let it fuzz. if you are an open source, Google provides machines for that. Like there is a dedicated cluster of machines that just fuzzes open source projects, and you can just set up your project. These are links to the documentation on how to get started with Go, and these will get you started so you don't have to spend to make it cover your code with fuzz. And here is the question. And I like something that when the first time that I gave this talk, it was a year and a half ago, and this was not a thing. Like the only way to fuzz was with the external tool, GoFuzz, and a lot of people asked me, why is this not part of the standard tool chain? Like, why is this not part of testing, of the testing package? Well, there was a proposal, it was accepted, the security team is already working on it, the Go team is already working on it, and here are some links to stuff that you can already try. And here is an example. So if you get the Go tip tool, which I strongly advise to use because it's amazing to use the bleeding edge. Well, what's more than the bleeding edge? There is the cutting edge, bleeding edge, I guess bone edge, whatever. The closer you get, the better to Go. So you can use the latest version and you can download a branch. If you update this tool, the latest version of this tool allows you to download a specific branch. And if you downloaded the dev.fuzz branch, you can already write your tests in this way. Now, if you look at this looks like a unit test. Like this is very Go. And instead of using test my function, you just write fuzz my function. Instead of taking a testing.t, you take a testing.f. And then it's just very simple. You add to the corpus by calling f.add everything that you think should be in there. And then you run f.fuzz that takes a testing.t. This is important because from now on, everything is exactly like your unit tests. So there is nothing different from the unit test that you're used to use and that you're used to write. The only different line is adding to the corpus. And this runs. Currently, there are some issues. Of course, this is a prototype, so it's not performant and the mutator might not be as smart as the GoFuzz external tool. But this is promising because this means that very soon, probably 1.18, I would say, but there is no commitment by the Go team on these. We will get to write fuzz targets in the same way that we write test targets. And this was the talk. So you can find the slides in the link at club.page.link/gofuzz. I would like to thank Egon and QBShy, Egon Elbre and QBShy for making the gophers, which are amazing and cute, especially the fuzzy gopher, the one with the fuzzy hair and the shield with a dice on it, which was made custom for fuzzing because, you know, you use random to protect your code. So it was a nice concept by Egon. And if you have any questions, you can ask it to me now or on Twitter at that link.
Thank you very much, Rob. If anyone's got any questions, feel free to unmute yourself and ask away if you like.
If there are no questions, I can get a bit in the details of the fuzz target for the cache that I was talking about. So basically, what I did was I had a byte slice. Is this readable or is this too small? Maybe you can zoom a bit more.
It's readable for me anyway.
Okay.
Yeah, it looks good.
Looks good.
Okay, thanks. So I had this byte slice and I had to return operations. So the first thing I did was, if you gave me too many operations, let's just abort. It's not my cache is not parsing anything. It's just storing stuff. And I know that if you give me too much, the cache is going to grow too much. And then I discarded input that was too short because I didn't get enough to transform in operation. And then what I did was something very simple, which was use some bytes to decide if the operation is basically get or put. And then the rest of the bytes were the data. So a key that I would take from the bytes, a value that I would take from the bytes, and the operation, which was either add to the cache or read from the cache, which I took from the first byte. And I kept looping. So every block of 9 bytes, I would create a new operation, and I would just return this sequence of operations. And the fuzz target, I would translate I would call this function, and then I would just call my new cache, instantiate the cache, and I would then compare the behavior of a map with the behavior of my cache. So as I was saying, if I have to check if it is in the map. If it is not in the map, I have to control what is going on. If the cache, like for example, this is the case, the cache is smaller than its capacity, so it should store everything. It should not lose any data. But if I miss, so if something is in the map, this is okay with 2Ks. If something is in the map but is not in the cache, then I call barf. Now, barf is a function that I called like this because it's just a wrapper around panic. The reason I created barf is because when I run this in a reproduce mode, it logs a lot more data. If it is just in fuzz mode, it logs the bare minimum that is required for me to find this issue. This is not needed. You can just panic here. And this is it. These are all the operations of the cache, and everything that I did was take this initial byte slice and translate it for something that made sense for me. Now, the new spec and the new proposal, which is this one, currently takes a byte slice, but in the future will take structs, will take ints, will take strings. So you will probably not have to do this translation work by hand. The standard library will do it for you. Okay, I don't see any questions in the chat.
No, anyone who wants to, you can unmute yourself if you like as well.
Okay.
No questions. Yeah.
So I guess if anyone has more questions, you can find me on Twitter. Otherwise, thanks for coming and thanks for listening to me.
Yeah. Thank you very much, Rob. That was fantastic talk.
Yeah,
as
thanks
always.
for having me.
Thank you, indeed. Okay. So what's left for me to let you all know then is we'll have another meetup next month. We haven't got a date yet or a speaker. So if anyone's interested, get in touch with Alan at BelfastGophers, and I'm sure we can fit you in somewhere. And other than that, then thank you very much for coming. Thanks again to Rob. Hope you enjoyed that chat, and hopefully we'll see you all again soon. Thank you.